Now let's proceed with Chapter 9, the Data Design Chapter. This is an important one. The chapter objectives are to explain file-oriented systems and how they differ from database management systems, or DBMS. Explain data design terminology including entities, fields, common fields, records, files, tables, and key fields. Describe data relationships. Draw an entity relationship, or ERD diagram. Define cardinality and use cardinality notation. So then we're going to explain the concept of normalization. This will carry with you. The concepts of normalization and some of the different levels of normalization should stay with you throughout your IT career. Explain the importance of codes and describe various coding schemes. Explain data warehousing and data mining. Differentiate between logical and physical storage and records. Explain data control measures. Now we're going to go into data design concepts, and we're going to begin with data structures. Data structures are a framework for organizing, storing, and managing data. It consists of files or tables that interact in various ways. Each file or table contains data about people, places, things, or events. So basically, this is kind of a logical view of what your database is going to be. So here are some examples right now. Mario and Danica. So Mario has an auto shop and Danica has an auto shop. Mario relies on two separate file-oriented systems that store data in separate files that are not connected. The mechanics system, which is one of these systems, uses the mechanics file to store data about shop employees. The job system uses the job file to store data about the work performed at the shop. Now remember that these are completely separate systems. At Danica's auto shop, she uses a database management, or a DBMS, with two separate tables that are joined, so they act like one large table. In Danica's shop operations system, which is one system, the tables are linked by the mechanic number, which is a common field because it connects the tables, and we're going to see an example of that. Here's the example right here. So as you can see, in Mario's shop there are two distinct systems with keys that don't have anything to do with each other necessarily. Data has to be entered into this system, and data again has to be entered into this system. Whenever there's the manual of keying of data and it has to be duplicated, you introduce the chance of error. Whereas if you look at Danica's shop, it's a one-to-one relationship here. So the job is tied with the mechanic. So you can go from the job number and you can get the mechanic's full name and information in one select statement, whereas here you have to enter it in two systems and you still can't necessarily put things together without a lot of manual intervention, I should say. Is file processing still important? File processing handles large volumes of structured data on a regular basis, can be cost effective, and it's great for transaction processing. So when you're looking at file sizing and what have you with a database that can be dynamic, it's static, it's a fixed size. If it's dynamic, it can grow dynamically, so as it needs to, that means. The database environment, or the DBMS, is the collection of tools, features, and interfaces that enable users to add, update, manage, access, and analyze data. I feel like I said analyze twice. Basically, there are a lot of different database management systems out there. You've heard of Microsoft SQL, you've heard of Oracle. There's also some user-supported database management systems such as Postgres, such as MySQL, just to name a few. Here's an example of a credit card company that posts thousands of transactions and how one might consider a file processing option. So you can see how that's demonstrated. The DBMS advantages. Scalability. The system can be expanded, modified, or downsized, and that really makes it really easy with dynamic file sizing, like I said. Economy of scale. Database design allows better utilization of hardware. So, in other words, with a database, you don't have redundant data, therefore your hardware will be much more efficiently used. Your disk drive's not going to fill up because you're not going to have duplicate information. Enterprise-wide application. A database administrator, or DBA, assesses the overall requirements and maintains the database for the entire organization. So, or for the entire application, I should say, or organization. It could be one and the same if it's an enterprise-wide system, such as the Alberta Student Information System. That would be considered enterprise-wide. And they do have a database administrator who's responsible for keeping the system up and running, keeping the files properly sized. I'm actually going to try and get this DBA to speak with the on-ground class at some point, if possible. If I do, and I can reserve that, I'll definitely have an email sent to the online students and invite you to join. Another advantage is better security. The DBA ensures only that legitimate users have access, and that's important. Data independence. Systems that interact with DBMSs are relatively independent of how the physical data is maintained. The design provides the DBA flexibility to alter data structure without modifying the systems that use the data. So that's part of your file resizing and that sort of thing. Let's start discussing the DBMS components. Users, database administrators, and related information systems. So like I said, if you have an ERP system or some other type of system that you need a database to support, it'll connect to the database management system, and it'll be the security, the integrity of the data, the sizing of the system will be handled by the database administrators. And the users are the everyday people who either update the database by updating forms inside the application or running predefined queries and what have you. Those are usually called operators or system operators. You hear the position computer operator. Oftentimes that's what they do. And a lot of times computer operators can get quite good at understanding the different queries and how they operate and what they do. Data manipulation language, or DML, controls database operations including storing, retrieving, updating, and deleting data. The schema is the complete definition of a database, including the description of all fields, tables, and relationships. So different databases can have different schemas associated with them. There's the physical data repository, and this is a complete definition of a database, including the description of all fields, tables, and relationships, views, and it is called the schema. So think of it as the physical data repository. Overview. A data manipulation language, or DML, controls database operations, including storing, retrieving, and updating and deleting data. Connecting to the web. The objective is to connect the database to the web and enable data to be retrieved and updated. Now, we've talked about the concept of middleware. This is software that integrates different applications and allows them to exchange data and interpret client requests in HTML form, then translate the requests into commands that the database can execute. Nowadays, middleware is still a really big deal. We also have the idea of a RESTful service, which is kind of a de facto standard now, but it is on its way to becoming a de jure standard for connecting and tying unlike systems together in a standard where they can communicate. So RESTful services are kind of something I'd like to mention here as well. I'm not going to put any questions on it or anything like that, but that's something a newer edition of this book would likely have. Web-based data design. So you got global access, ease of use, multiple platforms. It can be cost effective. Security can be an issue. It's the web, so you have to consider that. But you'll have security set up and you'll have people who are diligently looking into it. And adaptability issues. So that's something else. The internet offers many advantages in terms of access, connectivity, and flexibility. So migrating a traditional database designed to the web can require a lot of modification and additional software. Some of that software could be middleware. A lot of it can be different proprietary tools that allow the database to connect with their application. This picture here shows an example of a sample flow of a web page request in which information is updated. This shows that the web server uses middleware and it generates a data query to the database server, and the database server responds. Then the middleware translates the database response and converts it into HTML that your browser can read. So that's what's going on here in this example. I'll wait for just a second after I'm done speaking so you can kind of study and get the idea yourself. But that's a sample of what middleware does. So it really acts as an intermediary between two different systems. Now let's go through some terminology, and these terms are the same or almost the same as they would be in a database management system. So starting with entity, it's a person, place, or thing, or an event for which data is collected and maintained. So an event could be a transaction. You'd have a transaction entity. A thing could be a warehouse item. A place could mean a location. Maybe you have two warehouses, one in Atlanta, maybe you have one in Tacoma, Washington. A person, that could be a customer, that could be an employee, that could be just about anybody. So an entity is a person, place, thing, or event for which data is collected and maintained. Table or file. A table or file contains a set of related records that stores data about a specific entity. So if you had a person file, that person file might contain a gender field, it might contain a date of birth field, it might contain a zip code field for that person, although that would likely go under address, which is a place, and that would be linked. We'll see how that's done shortly. So I've started talking about fields. So let's say what a field or an attribute is. It's a single characteristic about a fact or entity. So a field is usually stored in a column, and like I said, something like date of birth, social security number, gender, maybe something like zip code, except like I said, that maybe would go under a different entity, like a place entity, like an address. So, but that would be a field inside the address file. A record, also called a tuple or couple, I've never heard it rhyming with couple, is a set of related fields that describe one instance or occurrence of an entity, such as one customer record, one order, one transaction record, one address record. Those would be individual layouts and individual items. And it's a set of related fields, or columns as they're referred to in SQL databases. So now let's talk about different types of key fields. We have the primary key, the candidate key, the foreign key, and the secondary key. So the primary key is a field or combination of fields that uniquely and minimally identifies a particular member of an entity. A candidate key is any field that could serve as a primary key. A foreign key is a common field that exists in one or more tables and can be used to form a relationship or link between tables. And a secondary key is a field or combination of fields that can be used to access or retrieve records. So let's take a look. Let's break these down a little bit here. So the primary key, we were talking about the person file earlier, or a person table. So if you have a person file or person table, you have social security number, which I mentioned. That could be a primary key. It's unique and it minimally identifies a member of an entity. So there's nobody who has the same social security or tax ID number. So that could serve as an excellent primary key due to its uniqueness. A candidate key is any field that could serve as a primary key. So let's say you have a member ID number that's also stored inside the person file, or you have a subscription ID number that's stored within the person file. You're using the social number as the primary key, but you could also use that number. So that number or that value is known as a candidate. So it's a candidate key. It's not being used as the primary key, but it could. A foreign key is a field that exists in more than one table and can be used to form a relationship or link between the tables. So I've been talking about this address example. So let's say your table has a field called address ID, which is stored inside your person field. So that would be a secondary key in the person file or person table, but on the other side you've got your address, which should probably be a primary key there. So with this foreign key or secondary key, which can also be used, you can form this relationship between the two different tables. And a secondary key is a field or combination of fields that can be used to access or retrieve records. Please, before I go on, please understand and get to know these key fields and concepts. I've given you a brief overview, but make sure you do some of your own reading, maybe outside the textbook even, because those concepts are going to stay with you. They're very important. Referential integrity is a set of rules that avoids data inconsistency and quality problems in a relational database. Referential integrity means that a foreign key value cannot be entered in one table unless it matches an existing primary key in another table. So we talked about the address value, right? We talked about the person address as a field or attribute in the person table. And we talked about having an address table, which would have the address ID as the primary key. So what this is saying is you can't have a foreign key value unless it matches a primary key in that table. So when you're putting in the person address, if you don't have that address key doesn't match with anything from the address table, no, you can't do it. And here is figure 9. If you want to hear, I'll wait and get to understand what they're saying here, because it's the same example of what they're saying. And here's where you could check this in Microsoft Access. Now let's talk about ERDs, or entity relationship diagrams. The first step is to list the entities that you've identified during the systems analysis phase, and then to consider the nature of the relationships to them. So when you have these relationships, you can have one-to-many, one-to-one, or many-to-many. So if we look at this here, a doctor treats patients. So you've got doctor. A doctor treats patients. You've got an example of the relationships here. So a doctor can treat many patients. So there's one doctor, but this doctor would have many patients. A patient can also have many doctors. So that's the example of how these relationship diagrams are designed. And here's some examples of some ERDs. Rather than have me read this over, I'm going to say exactly what's here. So these show examples of one-to-one relationships. So take a minute, look that over, and I'll continue on. And here is an example of the notation for one-to-many, which is also listed here. And again, I'll give you just a second. Many-to-many relationships are abbreviated as M to N, and here's some examples of that. It exists when one instance of the first entity can relate to many instances of the second entity, or one instance of the second entity can relate to many instances of the first entity. So take a look here and you'll get a better understanding of what we're saying. Just if you take this and here we have an example of an ERD, but it's a complex ERD. It shows multiple types of entity relations and how they're connected. So you'll notice that the diamonds are verbs and the boxes are nouns. You'll notice that there's different types of relationships here, and that's what this is trying to show, the big picture. So cardinality describes the numeric relationship between two entities and shows how the instances of one entity can relate to the instances of another. That's referred to as cardinality. And there's a diagram with what's called crow's foot notation on the right here. And I find it very difficult to remember this. I don't see the point in crow's foot notation, but it is common, so you are going to have to know it. When you take your midterm in this class, if there is any question on this, it will be something that you'll be able to do open book. So that being said, continuing on, here's an example of an ERD with the different notation symbols here, and I'll give you a second to look that over. And here is a sample library system, and it's using the crow's foot notation. And again, I find this very difficult. I'd rather see the numbers. However, continuing on to the different types of normalization. So first, what is normalization? It's the process of creating table designs by assigning specific fields or attributes to each table in the database. Normalization involves applying a set of rules that can help you identify and correct inherent problems and complexities in your table designs. The normalization process typically involves 4 stages: unnormalized design, first normal, second normal, and third normal form. So we're going to see what an unnormalized database or an unnormalized design looks like, and we're going to see its simplicities, yet we're also going to see its weaknesses. And when you're designing a system in the first place, if you don't have a good analysis up front, you can find yourself creating an unnormalized database due to lack of preparation and lack of planning. Lack of understanding what the data is supposed to look like. So to start, there's standard notation format. It starts with the name of the table, followed by a parenthetical expression that contains the field names separated by commas. The primary key fields are underlined. So here's an example. So you've got the name of the table, there's a name here, right here. You got field 1, which is also the primary key because it's underlined, and you got field 2 and field 3. So remember, these are fields or attributes, and they're in a database, these would be columns as well. A repeating group is a set of one or more fields that can occur any number of times in a single record, with each occurrence having different values. Let's go back to the address example for a second. How many of you have had to fill out addresses with 3 lines? That's what my address is. It's my name, which isn't even an address line really, that would be person field information. And then you would actually use your keys, your foreign key and your secondary keys, to create the connection to the address file, and from that I would pull 2 address lines possibly. So one address line would be my address, my second line would be city, state, zip. However, in different parts of the country, different parts of the world, addresses might be 4-line addresses or 5-line addresses. So that is something to keep in mind. So a repeating group is a set of 1 or more fields that can occur any number of times in a single record, with each occurrence having a different value. So for example, address line 1 being 125 Main Street, and line 2 of the address line 2 being apartment 605, let's say. So you could also have more address lines there, like I said, depending on the country, depending on different areas, how addresses are written. So here's an example of what we're talking about right here. So in an unnormalized database, you've got one order, you've got a date that's constant, you've got a description and a product number that are not. So these have repeating groups. This is what we were talking about right here. And just as an FYI, when you're doing a database and designing a database, these holes represent wasted space, and they can create inefficiencies in your database, both in size and responsiveness. So that being said, this is an example of unnormalized information, unnormalized database. Now we're going to go ahead and we're going to discuss first normal form, or 1NF. A table is in first normal form if it does not contain a repeating group. When you eliminate the repeating group, additional records emerge, one for each combination of a specific order and a specific product. The result is more records, but a greatly simplified design. So we're going to take a look at something really similar now, but in first normal form. So right here you have this information. It's still in first normal form. You have multiple order numbers here. So you have these 3 order numbers, which are the same. You have the product numbers, which are the same. You just have basically filled in the holes from where you were before. So there's no repeating groups. The primary key is a unique number combination of 2 foreign key values, order and product number. So that's what I figured they'd do. So they're taking this number and they're adding it to this to create the primary key. So it's a calculated primary key. All fields depend on the primary key, but some fields do not depend on the whole key, only part of it. So for this description here, we care about the whole thing. Of course we do. Actually, we only care about the product number. And whereas if we want to look at the supplier name, we probably could revert that to the product as well. The date is something that would be represented by the whole key. So a lot of this is ridiculous and a lot of this is redundant, but this is an example of first normal form. It is much better than unnormalized data. Now let's go on and talk about second normal form, or 2NF. You must understand the concept of functional dependence. Field A is functionally dependent on field B if the value of field A depends on field B. A date value is functionally dependent on an order because of a specific order number. There can only be one date. Objective is to break the original table into 2 or more tables and reassign the fields so that each non-key field will depend on the entire primary key in its table. So what does that mean? Let's take a look, because now we've seen 0NF, which is unnormalized, and we've seen first normal form, which is 1NF, where it's all been all the information has been contained in one table, but for this type of information it really needs to be broken down more. So let's take a look at second normal form. Now let's look at this example of second normal form. You can see that we've broken this down into the order table, the product table, and the order line table. So the information is all still contained, however it's much more broken down, it's much more concise. This makes for faster retrieval, makes for better storage. So now we're looking at all this where the fields are functionally dependent on a primary key. So here you've got the order number right here, and here you've got an order number right here. So your order line really is the primary key, is the unique combination of these two foreign keys. So let's continue and look at third normal form now. In third normal form, if every non-key field depends on the key, the whole key and nothing but the key. I like that. A third normal form design avoids redundancy and data integrity problems that can exist in second normal form designs. So when we're talking about redundancy, anytime there's redundancy, you have a data integrity risk. So let's look at the redundancy here. Where is that redundancy? You're seeing in this file, this table here, you're seeing order number being listed redundantly. You're seeing the product listed redundantly. So these tables look okay. So let's continue on and see what it comes out, how it comes out here. So here you've got the supplier number, so we can turn that into a fourth table and we can clean that up a little bit. Whoops, excuse me. You have products in second normal form where this is all broken out right here. Here it's split out because why do we need to list the same thing twice, as you can see right here? This is excessive, where here you've got a supplier file and a product file, and you've got unique keys that exist in both of these files. Actually, I'm sorry, these would be the unique keys right here. Here, let's take a look at the Crossroad College example. So this is unnormalized right now. Why? You got big gaps here. So here, let's continue on and look at the students file now with the gaps filled in, which is what we pretty much did to create the first normal form example. So I'll give you a second to look this slide over. Alright, I think that's enough time. Now let's continue on and I'll give you the opportunity to look at it in second normal form. So what are they going to break out next time? I'm thinking they're going to break out the advisor. What do you say? Let's take a look and study this. And here we go. Look at that, I was right. They created a table just for advisor. And this is a third normal form example right here. And here we have this example where we continue tying this together with our entity relationship diagram for the example we just looked at. So take a minute and look this over. And here we will go ahead and look at the magic maintenance example here. Notice that you have a key here. This will show you what your keys are and your primary keys, what have you. You've got, this is your one-to-many relationship example here. In these next couple slides, we're going to suppose that you work in an IT department and the sales team is looking for answers to specific questions. This is a very, very common scenario. In fact, this is a scenario that's occurring inside my company as we speak. They're actually looking for somebody to do these types of queries. And I could do that, but there's just way too much other work that I have to do. So read some of these bullet points over and then go over the next couple slides, and feel free to pause this video as you go and make sure that you understand what they're trying to do to accomplish these different tasks. And see, you won't learn the query language of SQL so much, but you'll see how the relations are made, and that's what's important in this chapter. Should I use codes, or should you use codes? A lot of times, yes, that's the quick answer. Codes can represent data that they are shorter than data they represent. They save storage space and cost, reduce data transmission time, and decrease data entry time. Codes can be used to reveal or conceal information. Codes can reduce data input errors. Coded data is easier to remember. The code itself can provide immediate verification that the entry is correct. So we're going to see some examples of what these bullet points mean as we move along here. So types of codes. Codes should be easy to learn and apply. They might be sequence codes, which are numbers or letters assigned in a specific order. They contain no additional information other than an indication of order of entry into this system. So I can think of an example of a sequence code right now, and that would be your student ID number here at Albertus. If you look at those numbers, I can tell if your number starts with the number 4, I can tell that you've been at school for less time than somebody whose numbers start with 3 and a 9. So going along like that, I can get an idea looking at the numbers of someone's student ID as to whether they're in their junior year or their sophomore year or their senior year. Kind of indirectly, some people don't take full loads, others do, obviously, but that's something that you can use as an example of a sequence code. So block sequence codes use numbers for different classifications. So think of it like the Dewey Decimal System. There's 100 level courses, which are freshman level, 200 level courses, which are sophomore level, 300 level, 400 level, and so on. So when we consider 100 level classes, that doesn't mean it's an easy class. A lot of times your 100 level classes might be harder. That's a little off the subject, but just something I wanted to throw out there. So it represents block sequence codes, so you can use your different class course levels. Alphabetic codes use alphabetic letters to distinguish one item from another. There's category codes, which identify a group of related items, whereas a department store might use a 2-character category code to identify the department. So maybe MS would be men's shoes, maybe WS would be women's shoes. I'm really oversimplifying that, but that's the idea. I've never worked in a department store, so I don't have a good understanding of. Abbreviation codes are alphabetic abbreviations, and state codes are an excellent example of this here. And some abbreviation codes are called mnemonic codes, and this is because they use specific combinations of letters that are easy to remember. And sometimes a mnemonic code can get an interesting name. I know in the system that they use at Alberta's for the student information system, they have the ITCI screen. That's the code abbreviation for the screen, and it's for doing data imports. But when you talk to their support people or you talk to people in the field, they call it the itchy screen. So that's an example of a mnemonic code. Here's some codes that you might recognize. These are airport codes. So going on with types of codes, there's significant digit codes, which distinguish items by using a series of subgroups of digits. Postal codes are an example of this. There's derivation codes, which combine data from different items and attributes or characteristics. That's combining fields together. A keyword to encode a number is an example of a cipher code. So, for example, a retail store might use a 10-letter word such as campground to code wholesale prices, where the letter C represents 1, A represents 2, and so on and so on and so on. Thus, the code for grand would indicate that the store paid $562.90 for an item, because it represents the actual digits there. Action codes indicate what action is taken and what is associated with that item. So if you have F to file, you might have X to exit. So these are codes that you would hit for basically quick entry and quick exit from different screens and forms. So here's an example of a code that uses significant digits to pinpoint the location. So another code that would be an example of this would be a VIN number on an automobile. Here we have an example of a magazine subscriber code. So let's talk about designing codes. Keep codes concise. Allow for expansion. Keep codes stable. Make codes unique. Make codes sortable. Use simple structure. Avoid confusion. Make the code meaningful. Use a code for a single purpose. And keep codes consistent. Now let's discuss data storage and access tools and techniques. Companies use data warehousing and data mining as strategic tools to help manage the huge quantities of data they need for business. There's data warehousing and data mining. We're going to go through both of these. So a data warehouse is an integrated collection of data that can be collected in one place, and it can include what seems like it's unrelated, but it's all the company's information. That's all warehoused into one database. It usually contains much more summarized information. You wouldn't see a lot of transaction, but you'd see a lot of summary data in a data warehouse. Data mining looks for meaningful patterns of data and relationships when it searches through a lot of data, a large amount of data. Logical versus physical storage. When we think of physical storage, we think strictly hardware. This is the read heads, the write heads. This is physical media being written to secondary storage devices and network storage devices. Logical storage refers to the data as we see it and understand it. So it's more of an open view that is kind of easy to understand. It's easy to access, and it's how most of us get our information. Now we can discuss different types of data coding. There's EBSTIC, or Extended Binary Code Decimal, EBSTIC, and it's mostly used with mainframe computers. We're not going to focus on that too much. We also have the American Standard Code for Information Interchange, and that's pronounced ASCII. And we use ASCII quite a bit here, and it's a coding method used for most personal computers. And we're going to see binary representation as well. I'm going to bring up an ASCII table, which will probably have binary coding as well. So give me just a second. I'm off on another screen here. And I click in ASCII table, and bingo, I have an example right here, ready to go. And look at that, it wants me to install Adobe. Don't think so. Let's just look at this one right here. How does that sound? We'll just make it a little bit bigger here. So here we can see you have the different, you have the hexadecimal code, you have the ASCII code right here. So these are ASCII code numbers. So basically these numbers represent characters. So if we were to look at this right here, if we wanted to see the letter A, it's ASCII code 65. Next code we're going to look at is Unicode. Supports virtually all languages and has become a global standard. So this is an international coding format, whereas something like ASCII is an American code. So Unicode is really becoming the global standard. Storing dates. The Y2K issue. I was part of the Y2K issue. I did a lot of Y2K fixing, and it was boring. So what is that? So that's in the old days, to conserve disk space when it was really valuable. Dates were stored as 2-digit numbers, and then once Y2K happened, as we know, they needed to convert everything to a 4-digit number. So you could tell what was what as far as somebody's age. ISO is the International Organization for Standardization. It requires the format to be YYYY, so full 4-digit year, MM for the full month, and DD. So why do they do it this way? The quick answer is they do it and have the sorting like this. They have it like this for sorting purposes. It really makes sorting extremely easy. Data control. A well-designed database management system must provide built-in control and security features, including subschemas, passwords, encryption. You need audits, files, backup and recovery, and that's all very important. So something to keep in mind there. I'm now going to go through the chapter summary. A database consists of linked tables that form an overall data structure. A database management system, or DBMS, is a collection of tools, features, and interfaces that enable users to add, update, manage, access, and analyze data in a database. Database management systems designs are more powerful and flexible than traditional file-oriented systems. Database management system components include interfaces for users, database administrators, and related systems, a data manipulation language, a schema, and a physical data repository. In an information system, an entity, which is a person, place, thing, or event for which data is collected and maintained. A primary key, in an information, that's an entity. That is a person, place, thing, or event for which data is collected and maintained. A primary key is the field or field combination that uniquely and minimally identifies a specific record. A candidate key is a key that could serve as a primary key. An ERD, or Entity Relationship Diagram, is a graphic representation of all system entities and the relationships among them. The relationship between two entities is also referred to as its cardinality. Normalization is a process for avoiding problems in data design. Data design tasks include creating an initial ERD, assigning data elements to an entity, normalizing all tables and designs, and completing the data dictionary entries for files, records, and data elements. And normalization is important. I would say trying to get your files into third normal form is the most important. Otherwise, someone down the road is really going to have questions. A code is a set of letters or numbers used to represent data in a system. Logical storage is information seen through a user's eyes, regardless of how or where that information actually is stored or organized. Physical storage is hardware related and involves the physical reading and writing of binary data to physical media. File and database control measures include limiting access to the data, data encryption, backup and recovery procedures, audit trail files and tables, and internal audit fields. That concludes the end of our chapter. Thank you.